And a bond order of 1 for diatomic fluorine is consistent with what we've seen in the other theories. So it seems like this lines up with the other theories so far, and we think, why bother with 2 theories? Why bother is because when we look at this, there are 2 main advantages of the molecular orbital theory. The first one has to do with oxygen. When we look at oxygen, our 2 oxygen atoms on the outside have 6 valence electrons. 2 in the 2s and 4 in the 2p. When we combine these, we get 12 electrons to put in the molecule in the middle diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, we look at this and we say, okay, I have bonding electrons in the sigma 2s, the sigma 2p, and the pi 2p. My anti-bonding electrons are in the sigma star 2s and the pi star 2p. I can find the bond order. I have 2, 4, 6, 8 bonding electrons minus 2, 4 anti-bonding electrons divided by 2 is equal to 4 divided by 2 is equal to 2, the bond order for oxygen. So far this is consistent with what we've seen in other theories. But I want you to look at this orbital box diagram. When we were looking at atomic orbitals, we talked about paramagnetic and diamagnetic. What do those mean? We weren't supposed to compartmentalize that part, just the valence bond theory part. Para and diamagnetic. That goes back to when we were talking about electron configuration. They are on the first page of your notes from chapter 7 in your vocabulary words that you looked up and studied.
Paramagnetic. Unpaired electrons and weakly attracted to magnetic field.
Right. Paramagnetic says it has unpaired electrons and will be attracted to a magnet. Oxygen has a very unusual quality. Now, oxygen gas we can't see, but if we cool oxygen down till we get liquid oxygen, you can purchase liquid oxygen. It's a little expensive, but you can purchase it, and when you do, if you pour it on the table and put a magnet there, the oxygen is attracted to a magnet. It's awesome, right? So when you look at this, you say, well, then it has to be paramagnetic because it has paramagnetic behavior. It's attracted to a magnet. When you look at this, here are 2 unpaired electrons. Molecular orbital theory is the only theory that explains the paramagnetic behavior of oxygen. When we draw the Lewis structure for oxygen, 2, 4, 6, 8, 10, 12. There's no unpaired electrons in there. If we think about this with valence bond theory, sigma bond, pi bond, lone pair and hybrid orbitals, there's no unpaired electrons in there. So this is the only theory that explains the paramagnetic behavior of diatomic oxygen, and that makes this theory really important because it can explain what nothing else can. So that's the first thing that makes this more special and important than other theories. Now, in the objectives of this course, it says that you can generate molecular orbital diagrams. So this is what you have to do on the test. Draw the MO diagram and calculate the bond order. Now, chlorine is a 3rd period element. The 3s and the 3p come together just like the 2s and the 2p. So on the 2nd energy level, we get sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. So on the 3rd energy level, we'll get sigma 3s, sigma star 3s, sigma 3p, pi 3p, pi star 3p. Okay? It'll just be a 3 instead of a 2. So go ahead now, get with your groups and draw the molecular orbital diagram for diatomic chlorine.